Hi everyone and welcome again. This video I want to go over separable differential equations. So let's see what they are. This is probably the easiest one we can solve, but let's go over those and I'll solve some examples. So then you can go ahead and do the homework problems. Now, what is that? Let me just read the definition for you. It's a first order equation of the form dy dx equals to g of x times h of y. So you have a function with respect to x, which then the function with respect to y. When you see this, and as you notice, you're multiplying them to each other. This is said to be separable. Now, a separable first order differential equation can be written as an explicit differential form where the solution is easily obtained by integrating both sides. So basically you have to separate the variables and then integrate both sides. So when you start, you're going to be given an equation like this, g of x times h of y. Separating them is you take all the terms with y and put it with dy and all the terms with x and put it with dx. And then you just integrate both sides, take the integral of both sides. So you find the integral of p of y, you can call that h of y, and that equals to the integral of g of x is capital G of x plus c. Then you can isolate y if needed. Let's do an example so you can see how this works. If we have this equation dy dx equals to 1 plus e to the 2x. So then the solution, what you can do, well, you can just separate. Again, if I write the step here for you, you can say dy equals to 1 plus e to the 2x dx. I did separate the variables. Then what's left to do is just take the integral of both sides. So what you get, the right side becomes y, and the left side is just the integral of 1 is x, and the integral of e to the 2x is 1/2 e to the 2x, and don't forget the constant, always very important. So now the formal definition, again, you can write it as dy dx equals to g of x times h of y. This is said to be separable or to have separable variables. So now in these examples, let's see, the first one you have dy dx equals to xy squared e to the 3x plus 4y. And the second example, dy dx equals to y plus sine x are separable. This one is separable because you can separate the variables. But for this one, you won't be able to separate them because the term with x and y, they're not factors of each other. So let's see how this works. So in this case, f of xy is that if I separate them, I can say this is x e to the 3x is g of x, and y squared e to the 4y is h of y. And the way you can just refresh your memories of algebra, e to the 3x plus 4y can be written as e to the 3x times e to the 4y. So rules of exponents, or e to the an plus m is the same as a to the n times a to the m from algebra. However, the second equation, this one, there's no way you can express y plus sine x as a product of a function x times a function y. So that's not a separable differential equations. So now, how do you solve those? We kind of got an idea, but let's go over some examples here. A one parameter family of solutions usually given implicitly obtained by integrating both sides. P of y dy equals to g of x dx. Example, that's a very simple and nice example. Solve 1 plus x dy minus y dx equals to 0. So if you want to separate the variable, you can just divide, take first of all negative y dx to the other side, and then just divide both sides by y and 1 plus x. So we separate it like that. Dy over y equals to dx over 1 plus x. Then you take the integral of both sides. The integral of dy over y is just ln absolute value of y, and the integral of dx over 1 plus x is ln 1 absolute value of 1 plus x plus c. Do not forget that c, or I called it c1 here. Now, if we want to isolate y, we can say absolute value of raise both sides to the power of e. So no, the base is e. So just write e ln absolute value of y. So here, e ln absolute value of y, we know it's just absolute value of y. So that's how I got that. Equals to e to the power of ln absolute value of 1 plus x plus c. However, I put a note here for you. E to the power of ln absolute value of 1 plus x or x plus 1 can be written as e to the power of ln absolute value of x plus 1 times e to the power of c. And again, same rule that we used in the last example. The rules of exponents or laws of exponents, a to the power of n plus n can be written a to the power of n times a to the power of m, and that's what I did here. Now I want you to notice something also. E to the power of c1 is just a constant itself. So instead of writing e to the power of c1, you can easily change that to c. Now, if our goal is to isolate y, so y can be written as plus or minus e to the power of c1 times 1 plus x. And again, the definition of absolute value, we know that absolute value of 1 plus x is 1 plus x if x is greater than or equal to -1, and -1 plus x if x is less than 1. So the final answer here is going to be e equals to, again, once you write plus or minus e to the power of c, you can just say that's a constant, equals to c times x plus 1. It could be a negative constant or a positive constant. So you can simply say c here is plus or minus e to the power of c1, and that's the solution. Next example, dy dx equals to -x over y. Here you're given an initial value because we want to know what the constant is, the c. So again, separate the variables. You can cross multiply, you get y dy equals to -x dx. Take the integral of both sides. The integral of y dy is y squared over 2, and the integral of x dx is x squared over 2, but there's a negative sign, and of course plus c. To find the constant, substitute the given initial value. So let's see what happens. So we can come to this equation, and we know that y of 4 is -3. So when x is 4, y is -3. So you can substitute y by -3 and x by 4, and that's what I did here. Solve for c, and you get y squared equals to isolate y squared, and is a -x squared plus 25, because here you can multiply that by 25, and c is 25 over 2. So if you put 25 over 2, you see it's just simple arithmetic. 25 over 2, 2's cancel, and that's what you get. Now, if you want to solve for y, take square root of both sides, and you can say y is square root of 25 minus x squared, of course, the plus or minus, don't forget. Next example, e to the 2y minus y cosine x dy equals to e to the y sine 2x, initial value is given. Same thing, separate the variables. So you can write e to the y, 2y minus y, divide both sides by e to the y, and divide both sides by cosine x. So you end up with that. So e to the y minus y over y is sine 2x over cosine x. So now separate them. E to the y, you can probably kind of show it to you here what happens. E to the, let's put this note, e to the 2y minus y over e to the y. So you can say this is e to the 2y over e to the y minus y over e to the y. And that's just e to the 2y. When you divide, you subtract the exponent. So you just get e to the y, 2y minus y, which is y. And then this one, take it to the numerator and make the exponent negative. So what you get is negative y e to the negative y. And on the other hand, this one, let's do another note. So sine 2x, you know, from trigonometrics, to sine x cosine x. So if you substitute sine 2x by 2 sine x cosine x, then cosines cancel. Let me just write it for you. Sine 2x over cosine x is 2 sine x cosine x over cosine x, and the cosines cancel, and that's how I got 2 sine x. So you take the integral of 2 sine x. Now, what's the solution here? The general solution, the integral of e to the y, just e to the y. And this one, you know, you can do this by integration by parts. So review the integration by parts from calculus 2. So the integral of negative e to the y e to the negative y is y e to the negative y plus e to the negative y. And the integral of sine x is just negative cosine x. So plus c, don't forget. So now if you substitute the initial value, then you can solve for c. The initial value y of 0 is 0. So whenever x is 0, y is 0. And if you substitute those, you can solve for c, and c is going to be, well, before. Here you cannot isolate y, so that's why you just put the general solution. You can write it like that. Now sometimes we have an integral defined function. So it says a solution method for certain kind of differential equation may lead to an integral defined function. That means the solution is an integral itself. So for example, if g is continuous on some interval I containing x0 and x, then a solution of a simple initial value problem dy dx equals to g of x, then you have the initial value is defined as an integral. So now before I go over this example, I want to kind of go over this little note here, the fundamental theorem of calculus. It says if g of x equals to, g of x can be written like that as an integral function. Integral going from a to x f of d dt, and g of x is the area from a to x. Now, in this case, f is continuous on AB, and g of x equals to a to x on, so in the interval of AB is also continuous, so, and differentiable on the open interval AB. The derivative of g of that function is just f of x. Now let's look at the example. This example this case, we know we cannot, it's not very easy to find the integral of e to the negative x squared. So what you can do is use that form. So we know if dy dx equals to e to the power of negative x squared, then I can say the integral of dy dt times dt equals to the integral of 3 to x e to the negative t squared dt, because that's and that they are the same thing. Dy dt is just e to the power of negative t squared. Now in this case, you can say y of t from going from 3 to x is the same thing as that function taking the integral of both sides. So basically, that is the same thing as that. So if we write that as that, then we can say y of x minus y of 3 equals to, don't change that. So this is a general solution. So note the function to the power of negative t squared is continuous, but its antiderivative is not an elementary function. So basically the answer now, we have y of 3 equals to 5, then you can substitute y of 3 by 5, and this is going to give you the solution, which it contains an integral, and this is not simple to solve. It's not an elementary function. Okay, I think that's it for this lecture. Please try the homework problems, and I will do some examples for you in my next video. Thank you for watching, and I'll see you in my next video. Have a good one, everyone.